When we want to make a circle or a rectangle larger, that's no problem. We can just change the numbers in our call to ellipse or rect. But when we want to make a more complicated object larger, or a whole bunch of objects, then we want to use a transform called scale. Here's the basic idea. Suppose we have a coordinate system, and here I've translated it so it's located somewhere in the middle of the graphics window, and I want to draw a bear. I'm going to use the same bear in the same location that I used in the videos on translation and rotation, so here's the bear. Now let's suppose I translate the coordinate system, but now I want to draw the bear twice as large as before. All I have to do is make the coordinate system twice as large as it was before. Now when I draw the bear, it comes out 2 times as large. That's because every time processing sees an XY value for a vertex of the bear, it's interpreted with respect to this enlarged coordinate system, and so the values that come out are enlarged as well. Now we don't have to scale both axes by the same amount. Here's our starting bear again, here's a new position, and I will scale just the x-axis by 2 and leave the y-axis alone. With the coordinate system set up this way, if I now draw a bear, the bear comes out stretched by 2 in x, but unchanged in y. I could, of course, go the other way around. I could make y very stretched out, and I could actually squish x by scaling it by a value less than 1. So in this coordinate system, x is horizontally squished, y is stretched out, and we get a bear that is horizontally squished and vertically stretched. And in fact, it looks kind of like a wolf. This is still the bear, he's just scaled horizontally and vertically by different amounts. Of course, we can mix this scaling in with rotation as well. So here I've translated, rotated, and then scaled each of these systems, and I get bears that are translated, rotated, and scaled. You won't be surprised to learn that the name of the function call that does scaling is scale. It takes 2 arguments, x and y, and this tells processing how much to scale the x-axis and the y-axis. These 2 numbers are used to multiply the lengths of x and y. Let me show you what I mean. First, I'll draw our typical grid in the background of the graphics window, and now I'll scale the 2 axes by 3 and 2. To scale the x-axis by 3, that just means make it 3 times longer. To scale the y-axis by 2, it just means make that 2 times longer. And this now is our new coordinate system where x is 3 times the length it used to be and y is twice the length it used to be. Now let's do another scaling. Suppose that this is our system and I now call scale 0.5, 1.5. That says take the x-axis as it is now and scale it by 1/2. Well, right now it's 300 units wide, so if I scale it by 1/2, it's only 150 units long. The y-axis is 200 units. If I scale that by 1.5, that becomes 300 units, and now this is the coordinate system I use from now on. Let's take scale out for a spin and use it to draw a family of 3 bears walking up a slope. On the left edge, we have a normal-sized bear. In the middle, we have a bear that's stretched horizontally. And on the right, we have a bear that's been enlarged in x and y. And you'll notice that the bear also seems to be leaning forward a little bit, and we'll get to that. First, I'll label these big grid elements, so we have some idea of what the numbers are in our graphics window. As before, I'll put a piece of tracing paper in front of everything and start out with the coordinate system in the upper left. Let's now look at the code that will draw this picture. Here it is. It's a bunch of calls to translate, rotate, scale, and draw bear. Draw bear, as in the rotation and translation videos, just draws the bear in the orientation we just saw. So let's go ahead and dig in and draw the picture. First line tells us translate. The values 140 and 160 came from me monkeying around with the translation values until the coordinate system sat just underneath and in the middle of the smallest bear's legs. So, okay, if we translate then by 140 in x, 160 in y, remember we always translate following the x and y axes where they're pointing now. Once we start rotating, they're going to be pointed in other directions, but right now x goes to the right, y goes down, so we'll move to the right and down, and that puts us right where we want to be between the bear's legs. Now I want to rotate the coordinate system because the bear is walking uphill, and I measured that with my little protractor, and it looked like just about minus 20 degrees. So I convert that to radians and hand it to rotate, and now the little coordinate system is in the right place, and I'm ready to draw the bear. So now we've completed our first bear. Let's move on to bear number 2, and we'll have a chance to see some scaling. So first things first, we need to translate. Now here we're going to translate along the red arrow and the green arrow. And notice that they've been rotated. So when I translate 145 in the red arrow, I'm going to be moving both to the right and up. And when I move 11 units in the direction of the green arrow, I'm moving down and right. So okay, if we carry out this translation, it puts us right where we want to be underneath the bear. And now we look at the next step, which tells us rotate. And when I measured this, it looked like about 10 degrees because the hill is flattening out a little bit. So, okay, I'm going to rotate 10 degrees clockwise. I hand that to radians to get the value in radians and hand that to rotate, and that rotates the coordinate system. Now we have our first scaling operation. I'm going to scale x in 2 and y in 1. That says I'm going to take the length of the red arrow, the x arrow, and multiply it by 2. I'm going to take the length of the green arrow and multiply it by 1. So the green arrow won't change, but the red arrow will get twice as long. So let's go ahead and do that. Now the red arrow is twice as long as it was before. We advance to the next line of the program, and it says draw bear. Well, we know that the bear is going to be twice as wide as he is high because we've just stretched out the x-axis. So let's go ahead and draw that bear, and sure enough, it's a very long bear. Now we move to the next line. It tells us translate, but this is a kind of a funny moment. Look at the previous translation calls. We were translating by 140 and then by 145. And we clearly want to go at least that far to get to the next bear. In fact, we want to go about 200 units. But we don't translate by 200 units because the x-axis now is twice as big as it used to be. To move 200 units along the x-axis, because the x-axis is now double length, we only move 100 units. You can think of this as saying, how many copies of the x-axis do I need to lay one after the other to get where I want to go? Well, the x-axis is now twice as long as it was before, so we only need half as many copies. This might seem a little bit weird to you, and if it does, that's fine. It is kind of a weird concept, but you'll get used to it very quickly once you start playing around with it yourself. We'll come back to it again before the end of this video, and we'll also see it again in the video on transform techniques. So right now we're going to translate by 100 units along the current x-axis and 15 units along the y-axis. So that moves us up and to the right and then down and to the right a little bit. That puts us right where we want to be. Now we need to rotate to get to the level field where the bear is walking. Now we need to rotate again because the hill has leveled off. So I measured it and I thought, okay, about 10 degrees because the hill looks pretty flat. But watch what happens now when I rotate by 10 degrees. Something weird is going to happen. Keep your eye particularly on the y-axis or the green arrow. And now we'll rotate. And look what happened. The green arrow and the red arrow are no longer at 90 degrees. They no longer form a right angle the way they used to. This is perfectly normal. This is what happens when you scale unequally in the x and y axes and then you do a rotation. We'll come back to this. But okay, now that we have this coordinate system, let's go ahead and do some scaling. In this case, I will scale in y by 2, but in x by 1. So the length of the x arrow won't change, but the length of the y arrow gets longer. And now, when I draw the last bear, the bear is larger in x and larger in y, and it's a double-sized bear. But the bear is leaning forward a little bit. This actually has a name. We call it skew or shear. And like I said, this is a perfectly natural thing that happens when you scale by unequal amounts in x and y and then rotate. People use shear all the time because it's a great effect. It's a great kind of a transformation. It's a way to get the bear to do exactly this, for example, to get things to look like they're leaning forward. So if you want your objects to be skewed or sheared, you'll do this kind of thing, the unequal scaling followed by a rotation. If you don't want it, then never do unequal scaling. Always scale the x and y axes by the same amounts, and skew or shear will never show up. In all of the function calls I've been writing so far, I've been calling scale with two values, x and y. If you want to scale both axes by the same amount, there's a shortcut. You can just say scale and give it a single number. And that value will be applied to both the x and y axes. Saying scale f is exactly the same as saying scale f, comma f. It's just a little shortcut.